Hello everyone, I'm Asim Jakar, co-founder Exploity, and today we are going to be talking about terrestrial trunked radio protocol security, or TETRA as it's more commonly known. And we have with us today Jos Wetzels, co-founder Midnight Blue. Jos, thank you for coming down to ISMG studio.
My pleasure.
So let's talk about your latest research where you found vulnerabilities in TETRA's end-to-end encryption. So what were the core architectural and implementation flaws that you uncovered in the end-to-end encryption? And can you also talk about the risks and the impact of the same?
Yes. So for those unfamiliar with it, TETRA essentially has two layers of security. There's the air interface encryption, which is the regular layer of security that's used by all the users, which we did research on 2 years ago, found several flaws. And then there's the end-to-end encryption, which is essentially the layer that's used for the most sensitive use cases, such as intelligence agencies, special forces, covert units. Both of these layers initially have been kept proprietary and secret. Usually this is an indication that, something's going on. Either designs are not up to standard or there are vulnerabilities. We found some of these vulnerabilities in the air interface encryption 2 years ago. We followed up by reverse engineering the end-to-end encryption layer and discovered several issues. One of the issues is that, as with the air interface encryption algorithms, there is a weakened variant of the algorithm where they essentially take the 128-bit key and they reduce it to 56 bits of security for export control reasons. Now, this is obviously devastatingly weakened. It's not going to add any actual protection, especially for these sensitive use cases. And we also found some flaws at the protocol design level. For example, the ability to replay, but also inject voice traffic, as well as replay text messages. And the risks, especially in these high-end use cases, are fairly severe, especially when it's about this weakened algorithm. It allows you to basically strip off that entire layer and do whatever you want with the layers below that.
Did you find that any evidence of any custom encryption that they were using, or was it like AES or standard encryption?
Yeah, so the protocol design was essentially kept secret and under NDA, so nobody really knew how it worked. And we talked to various stakeholders throughout the world, law enforcement agencies and so on. They had no idea how it worked. And when we reverse engineered it, it turned out that essentially most of the implementations use either AES or they use IDEA, which is an older algorithm. They also have an option for custom algorithms to swap them in. And the problems really weren't the cryptographic primitives. AES is fine, IDEA is fine, and most of these custom algorithms might be fine as well. It was at the protocol design level where these mistakes were made.
And can you also elaborate on the other vulnerabilities that you found in TETRA that are relevant to OT networks specifically, things like packet injection or multi-cipher network risks or insufficient patches for older vulnerabilities?
Yeah, so as part of this research, we didn't just focus on end-to-end, but also on the rest of the TETRA standard, because there were many issues still unexplored. One of those issues was the issue of packet injection. So 2 years ago, we noticed the theoretical possibility for attackers to inject network traffic on these TETRA networks when you've either cracked the key or obtained it in some other fashion through, for example, one of the key stream recovery attacks we found. Now, all of the vendors and ETSI, which is the standards organization responsible for TETRA, they basically said it's infeasible. You can do it in practice, which kind of irked us because we knew it was possible in practice. So we essentially made a lab setup, a realistic lab setup, and demonstrated the feasibility of these attacks. And what this allows you to do as an attacker is essentially inject malicious traffic directly into the TETRA network streams. And in the cases when you have SCADA telecontrol traffic being carried over TETRA, very often, in most of the cases that we saw, they rely only on TETRA to provide security. There's no VPNs carried on top of it. There's no serial end-to-end encryptors. So as soon as you break the TETRA security layers, you're directly in the OT networks. And one of the cases that we're going to demonstrate at our Blackout talk is the ability to inject malicious switching commands in an electric utility network. And for example, turn off the power at a substation in these kinds of scenarios.
Oh, wow. And what was your earlier research, TETRA burst, about, and what were the issues that you identified then?
So in TETRA burst, which is the research that we carried out 2 years ago, we did the first public analysis of TETRA in general, because nobody had looked at it in more than 20 years. It's an important technology. It's very widely deployed in over 100 countries, law enforcement, but also critical infrastructure. And what we did there is we looked at the air interface encryption, which is the basic layer of encryption. We managed to reverse engineer these secret cryptographic algorithms by getting them out of a radio. We bought a radio from eBay, found some zero-day vulnerabilities, managed to break a trusted execution environment, extract those algorithms, and then found several flaws, one of which was a backdoor in one of the algorithms, TEA1. Essentially, this is the algorithm that's used outside of, let's say, Western Europe. With some exceptions, there are some countries that are friendly with Western Europe, they get an other algorithm, but this algorithm is widely used outside of Western Europe and also in critical infrastructure inside of Europe. This backdoor, I think, was the big one, but we also found vulnerabilities in the way the air interface encryption schedules its cryptography, essentially.
Okay, and so this backdoor was more on the implementation side, or was it part of the protocol specification?
It was part of the design. It was a consciously designed backdoor as part of the Wassenaar export controls, which restrict the export of cryptography up until certain levels. The main issue there is that it was actually weaker than what export controls mandate. Export controls say you cannot export it unless it's 56 bits of security, but this backdoor essentially took an 80-bit key and it compressed it to 32 bits. Which can be cracked in less than a minute on a consumer laptop. We even demonstrated it on an old Pentium 2 from 1998, being able to crack it in several hours. So it's quite a bad situation.
So what lessons should engineers or developers working, especially those who are working on these proprietary and closed system, take from these disclosures that you made?
I think the main one, and this is a straightforward lesson, but still it doesn't get applied enough. Know what you buy. If you buy this technology and you rely on a certain security layer, you need to either fully know how it works yourself, or you need to have done an independent assessment to be able to ascertain that the level of security you assume it provides is actually provided. Secondly, a healthy dose of skepsis with regards to what the vendors tell you. We've had multiple reports of big critical infrastructure operators being sold TA1 even after the disclosures, where they said, it's going to be fine. Or they were told packet injection is impossible. And then when we were brought in to do an assessment, we showed that, many of these vendor claims simply weren't true. But after that, they've already rolled out some of these measures. So I think one of the big lessons is try to do this kind of security during as early as possible, during procurement, during factory acceptance test, during site acceptance test, because it's going to be much more expensive to address it if it's already out and deployed on the field.
Yeah. So from your perspective, which attack surfaces in modern industrial and wireless systems are still underestimated by defenders? And where do you see the next wave of research coming in?
Yeah, I think that's a good question. I think in general, industrial wireless is underexplored. There's a lot of proprietary solutions still. There's the more open protocols like ISA 101, wireless HART. People have looked at that. There's rough ideas about the security posture. But there's a lot of proprietary solutions by General Electric, by Schneider Electric that are used, for example, for communications between offshore platforms and onshore infrastructure. Nobody knows how they work. Nobody knows how the security of these things work. They're deployed in sensitive environments. I think there's a lot of attack surface to still explore there. I think with regards to the next wave of security research, I'm personally very interested in seeing these same patterns applied outside directly of OT, but also in autonomous vehicles, autonomous aviation units, drones, etc. I think there's a lot of similar problems that get repeated across industry verticals, and they get solved in one vertical, and people don't learn these basic lessons and apply them when they're standing up new systems. So I think there's a lot of the same stuff to be found in a lot of different verticals.
Yeah. I totally relate to that. So you've worked extensively on embedded and industrial systems. So when you start analyzing a black box device or a protocol, what's your typical approach from recon to exploitation, and how do you adapt it to constrained and undocumented systems?
Yeah, it varies from system to system, but typically one of the first approaches I like to take is just getting as much documentation as possible. Anything that is there, we should be able to obtain it, and that doesn't just go for like the official vendor manuals, but also data sheets for the controllers, data sheets for various components on the board. So we start by getting all the high level information, then getting a device, opening it up, doing a teardown through all the layers, documenting all the different components, seeing what information we can obtain. And then basically we move through the attack surface in order of priority. And these priorities depend on how the system is integrated in the setups and the networks of the client. For example, if the system interfaces through Ethernet with the client systems, that's the interface we'll prioritize and we'll first look at. Whereas, if it's a standalone system, we might look at JTAG first in order to be able to extract the firmware. So these priorities are always determined by how the system is actually integrated, because typically you don't have time to fully explore all of the attack surface. You have to focus on what really matters for the client and the client's integration conditions.
And so where do you see these OT equipment stands from a security perspective when compared to other things like IoT or autonomous vehicles or general enterprise equipment?
I mean, I think the embedded security in general lags a lot behind enterprise and conventional IT security. I mean, this goes for SOHO routers as much as it goes for PLCs, as it goes for a lot of stuff. But it's not impossible. I mean, if you look at certain parts of the embedded market, like gaming consoles, set-top boxes, what used to be smartphones, it's debatable whether they're still embedded, but they've really upped security posture over the last decade. So it is possible in these environments because the financial incentives are there. When it comes to OT, what I've seen over, let's say, the last 10 plus years, not a lot of progress is made. There's still a lot of devices that are hitting the market or that just hit the market with the bare minimum in security measures. Some improvements have been made compared to the past, as in now there's, maybe a password on the engineering interface, but then the problem is that standards just demand functional testing. So they say, is there a password? Somebody looks at the client, and they say, I see a password. But they don't check, is it client-side authentication? Is there any cryptographic binding? So there's really little incentive to build these robust security architectures from the scratch. Some vendors are making some bigger steps when it comes to, secure boot, etc. But it's a very slow march forward. And I think maybe it's a little pessimistic, but relying on endpoint device security and OT really getting up to the point where you want it to be is not a winning strategy. You need additional security controls around and on top of that if you want to secure an OT environment.
And do you think standards like 62443 or some of the IoT HC standards, are they helping create secure products, or it's just checklists?
I mean, they help in the sense that they provide some leverage in order to argue internally within a product company as to why you have to have certain security expenses, as SDLC stuff, invest in security training for your personnel. But when the evaluations for the product certification happen, it really depends on who is doing these evaluations and with what degree of quality. So I've done some research in the past on IC 62443 certified devices. They had various other certifications as well, like the General Electric Achilles certification. And these certifications require you to do fuzzing. So they were certified, we've been fuzzed. Yeah. And then when we started doing fuzzing, all these really trivial bugs started falling out, which lead me to question, how are they being fuzzed? If you just specify you need to do fuzzing, that's not good enough. You need to really have technically specific requirements on part of the standard in order to ensure that a vendor moves in the right direction. Otherwise, it becomes too checkboxy, in my opinion.
All right. Thank you so much. My pleasure, Jos. It was really great speaking to you.
Thank you.
This is Asim Jakar. We were talking about TETRA security with Jos Wetzels. I'm signing off from ISNG Studio.